The next unit we're going to undertake is called polynomial functions. You have studied polynomial functions quite a bit. You may have not recognized it. So let us define a polynomial function. A polynomial function can be written in the form y is equal to a n, x to the power of n, plus a n minus 1, x to the power of n minus 1, plus dot, 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 all the way to, you should say, a1x plus a naught. Now, an is known as the leading coefficient. N is known as the degree of the function. And a naught is the constant of the function, which translates to the y-intercept. Now, this is a definition that sometimes scares people, but there's really no need to be scared. So you've already dealt with 3 cases of polynomial functions. You've dealt with the constant polynomial function, y is equal to a constant. You've dealt with the linear, which is degree 1. And you've dealt with quadratic functions, which is degree 2. So allow me to give you some definitions of polynomial functions. Y is equal to 2x squared plus 5x plus 2. Surely you remember this from last year. My leading coefficient an, well, perhaps let's pick apart what's going on. N is the degree of the function. And n here is 2. The degree of the function is the largest exponent. an, the leading coefficient, well, an is the constant in front of the term that determines the degree. In other words, is the coefficient in front of the variable with the largest exponent. Now the y-intercept, which is known as the constant of the function, simply is the y-intercept or the constant. Now you've run into, so this would be quadratic, you've run into the constant function. Now this is degree 0 because y is equal to 4. And this is equivalent to y is equal to 4 to the power, or 4 x to the power of 0, because x to the power of 0 is 1. So we don't write that. We typically write y is equal to 4. Also, you know that y is equal to negative 2x plus 1, the linear function. The highest exponent on top of the x is 1. So this is a first degree polynomial function. The y-intercept is determined by the constant. The leading coefficient here is negative 2. Now the leading coefficient actually determines quite a bit about a linear function. We call it the slope. Also, the leading coefficient of this quadratic also determines something about the shape of a quadratic, and we say that if a was positive, it opened upwards. If a is negative, it opens downwards. And we are actually going to see this played out with other polynomial functions. And really, a polynomial function starts off with some exponent. So x to the power 6 plus maybe some coefficient, and the exponent is reduced by 1. And then the next exponent is reduced by 1. And if it doesn't exist, that would mean that the coefficient for x to the power 4 is 0, x to the power 3 is 0, x to the power 2 is 0, x to the power 1 is 0. So this is also a polynomial function. You're quite familiar with polynomial functions. Now, what's going on with polynomial functions? The following are some properties of polynomial functions. Suppose that we have degree n, that the largest exponent is n. The number of turning points will be n minus 1. Now, if you don't believe me, quadratic is a degree 2. how many turning points on a parabola? 1. The maximum number of zeros is n. So the most number of x-intercepts or zeros that we can have on a polynomial function is going to be equal to the degree. Now, if the function is even degree, the left-hand and right-hand side behavior mimic those of all other even degree functions. So all even degree functions on the left and the right anyways behave the same. On all odd degree functions, the left-hand and right-hand side behavior, that is the arms of the graph, will mimic those of other odd degree functions. Now, are you an expert in one odd degree function? Absolutely you are, and it's called a linear function. Last but not least, the y-intercepts are located at a0, or the constant term. So I'm just going to have some fun here. I hope it's fun. I'm going to start off with a constant function. Now, I'm going to maybe make my Cartesian plane on each of these. Hope that's okay with you. Now, what does a constant function look like? A constant function might look like this. So for instance, this might be y is equal to 4. Now this is just a sketch. On the other hand, this might be y is equal to -2. How many x-intercepts? 0. So the degree of this is 0. The maximum number of turning points is 0. There are no turning points here. And the maximum number of zeros is going to be 0. We're going to ignore the special case where y is equal to 0. Now a linear function, let's go on to the linear. Now a linear function, maybe I'm just going to, y is equal to 2x to the power of 1 plus 1, or y is equal to 2x plus 1. The degree of this is 1. The maximum number of turning points on a linear function, well, how many turning points are that where the function goes from increasing to decreasing? There are no turning points or vertexes on this. Same with this linear function, so they're just lines. But yet the maximum number of zeros that we can have in a linear function is 1. Now a quadratic function. We're very familiar with quadratic functions. So y is equal to 2x plus 3x plus 1. That would be an example of a quadratic. Now, we could have a quadratic that opens like that. Or alternatively, it could open like this. Or alternatively, a quadratic could look like this. So the degree of a quadratic is 2. The maximum number of turning points is 1. And a turning point on a parabola is called the vertex. The maximum number of zeros is going to be 2. But hopefully my drawing illustrates to you that we could have no x-intercepts. And when the vertex is on the x-axis, we have exactly 1. And then sometimes the way we draw it is my parabola actually has 2 x-intercepts. Right there and right there. So it's just the maximum. Also, parabolas don't always open up. They can also open downward. And the same logic holds that the maximum number of zeros is 2. Now, a cubic function. Cubic function, it is degree 3. So it might be y is equal to 3x to the power 3 plus 7x squared plus x minus 4. And I'm maybe going to get rid of that 3 just to reduce the ambiguity there. What makes it a degree 3 is the exponent. Now, what does a cubic equation look like? the graph of it might look like this. How many turning points on that? Well, what we see is 1, 2. What is the maximum number of zeros? So on a cubic, it is 1, 2, 3. It actually matches the degree. And that should make sense because if you have a cubic function, what are the maximum number of factors that you can have? And each factor would relate to a x-intercept using the zero product property would be 3. Also, I'm going to try to draw another cubic for you. A cubic can also look like this. It's weird. Anyways. Now, a quartic function, well, a quartic function might look like this. But a quartic function might also look like this. So what we see is a quartic function is degree 4. The maximum number of turning points is 3. So it's 1 less than the degree, but the maximum number of zeros is going to match the degree. Now, a quintic function is going to look, oh, did I do that right? I think I did that right. Quintic function might look like that. And before I get all crazy on you, what did I do? 1 turning point, 2 turning points, 3 turning points, 4 turning points. Ah, there we are. Now, that's my quintic function, and by the way, we could reflect it, but it's degree 5, maximum number of turning points is 4, maximum number of 0 is 5. So, where am I going with this? I've tried to make the connection that all odd degree functions behave the same. Now, what is true about all odd degree functions is that the left-hand and right-hand side point in different directions. What is true about even degree functions? Well, the left-hand side and the right-hand side both point in the same direction.